Hello everyone. Welcome back to my channel. How far could humans expand across the universe? It is late at night, and you are staring up at the clear sky, wondering just how far human beings could actually travel into the infinite reaches of the cosmos. Looking back at the staggering technological breakthroughs of the last few decades, it feels almost inevitable that we will soon build permanent outposts on neighboring worlds and eventually set sail for distant solar systems. When we project our imaginations far into the future, we naturally picture cinematic space operas filled with hyperdrives and warp engines, effortlessly hopping between distant galaxies without breaking a sweat. But as thrilling as those cinematic visions are, the reality dictated by physical law paints a radically different picture. There is a massive chasm between what our imaginations can dream up and what the fundamental laws of nature actually permit. A gap that we have not yet bridged and perhaps never fully will. To understand where we might end up, we have to start with where we are standing right now. Humanity has successfully walked on the surface of the moon, an achievement that remains one of the most technically demanding endeavors in history. Yet on a cosmic scale, our moon is practically in our own backyard at a distance of just 384,000 kilometers. Our most distant mechanical ambassadors are the Voyager spacecraft launched back in the 1970s, with Voyager 1 having officially crossed into interstellar space roughly 24 billion kilometers away from Earth. That distance sounds utterly monumental, yet moving at its current blinding speed, it would still take that tiny probe about 75,000 years just to reach Alpha Centauri, the very closest star system to our own sun. This immense void is where the true difficulty of deep space exploration begins to reveal itself. Before we can even realistically dream about reaching another star, we have to grasp the sheer scale of our local neighborhood. Our solar system is exponentially larger than most people imagine, with a single journey to Mars taking anywhere from 6 to 9 months using modern propulsion concepts. Reaching a gas giant like Jupiter represents an entirely different order of magnitude, demanding 5 to 6 years of constant travel with our current capabilities. Way out at the absolute boundary of our sun's gravitational grip lies the distant Oort cloud, a giant spherical shell of frozen objects extending up to 2 full light years into the void. Even within the confines of our own local cosmic backyard, there are vast distances that we simply cannot cross without forcing crews to wade across multiple generations. Establishing permanent human colonies on Mars, hovering around the moons of Jupiter, or mining the asteroid belt are all highly realistic milestones for the next 2 or 3 centuries because they are physically possible despite being immensely dangerous and expensive. Moving beyond our solar system to the stars, however, represents a completely different scale of existence. Alpha Centauri sits roughly 4.2 light-years away, and when you consider that a single light-year spans nearly 9.5 trillion kilometers, you realize that even our immediate stellar neighbor forces us to confront numbers that shatter human intuition. Even if we manage to build a revolutionary starship capable of traveling at 1% of the speed of light, an achievement vastly beyond our current engineering abilities, the journey to that single nearest star would still require 420 long years. Remember, Alpha Centauri is merely the closest point on a cosmic map, whereas our home galaxy, the Milky Way, spans a mind-boggling diameter of 100,000 light-years. Nearest major galactic neighbor, Andromeda, sits 2.5 million light-years away, while the observable universe stretches across an incomprehensible 93 billion light-years. These numbers are not just ridiculously massive, they are profoundly brutal because they demonstrate that no matter how brilliant our engineering becomes, the universe enforces a fundamental cosmic speed limit that nothing with mass can ever break. Yet throughout our history, humanity has never simply accepted a boundary without trying to push against it, which is why scientists are actively analyzing exotic propulsion systems like giant laser-driven light sails that could theoretically push miniature probes up to 20% of light speed. For larger crewed vessels, researchers are placing their long-term bets on nuclear fusion engines, harnessing the exact same nuclear process that powers the sun to propel ships at a respectable fraction of light speed. The ultimate theoretical threshold of propulsion remains antimatter engines, which would unlock the highest possible energy density in the universe, though producing and storing antimatter remains astronomically expensive and entirely out of reach for the foreseeable future. If we look back through human history, we are constantly reminded that scientific progress does not move in a predictable straight line, but rather leaps forward in sudden game-changing revolutions. 200 years ago, atmospheric flight was deemed impossible. A century ago, nuclear energy was science fiction. And 50 years ago, the idea of carrying a global supercomputer in your pocket was pure fantasy. To truly understand what high-speed interstellar travel might look like, we have to revisit the groundbreaking discoveries of Albert Einstein over a century ago, when he proved that time itself is not absolute. Einstein showed that as an object accelerates closer to the velocity of light, time actually ticks slower for that object relative to a stationary observer. This mind-bending reality means that an astronaut traveling toward a target star 100 light-years away at 99% of light speed would only experience roughly 14 years of passage inside the ship. However, back home on Earth, a full century would pass during that same trip, meaning that when the crew finally returns, their friends and families will have been gone for generations. While this extreme time dilation theoretically makes deep space voyages feasible within a single human lifetime, the engineering hurdle of energy generation remains colossal. Accelerating a starship to 99% of light speed would demand more energy than every power plant on Earth could produce combined over thousands of years of continuous operation. Beyond the massive energy requirements, anyone attempting to travel at relativistic speeds faces a terrifying second obstacle hiding in the dark, which is interstellar dust. When you are traveling at 99% of the speed of light, a microscopic speck of dust floating in the vacuum ceases to be harmless and instantly transforms into a devastating kinetic projectile. Colliding with a tiny particle no larger than a grain of sand at those speeds would unleash an explosive impact equivalent to a heavy bomb detonating directly against the hull. Designing a starship capable of surviving such a journey would require revolutionary deflector shields and structural materials that our current material science cannot even conceptualize. On top of the physical debris, cosmic radiation becomes deadly due to relativistic effects, as incoming harmless particles get shifted into lethal high-energy rays capable of penetrating standard armor. The crew inside would suffer fatal radiation poisoning almost instantly unless we engineer radically new force fields or electromagnetic barriers to deflect these invisible storms. These physical hurdles are extraordinary and deeply intimidating, yet none of them explicitly violate the known laws of physics, leaving the door to the cosmos open just a crack. Imagine standing in the year 2800, an era where humanity has mastered nuclear fusion, scaled up antimatter manufacturing, and created indestructible hull shielding capable of brushing off dust impacts like drops of rain. In this future, our descendants launch a flagship capable of accelerating to 99.9% of the speed of light, unlocking radical time dilation for everyone on board. For that fortunate crew, a deep space expedition towards star clusters located 1,000 light-years away would feel like a journey of just a few short decades. They could spend their lives charting exotic solar systems, searching distant worlds for alien life, and exploring the dense central hub of the Milky Way, all within a single career.